Make sure I've got enough sound. Yep. Okay, so I'm good, and we are on our way. Okay, so this first part is a looking at the lab 2, and I'll go to the website. And courses, EET 1020, and the lab manual. And we go down to page 16. So here's what we have, right? Any questions about that? And that's, put that over to the side. And get this going. So we want to be able to do this operation, okay? So I want to be able to do that operation. And I want an answer, and either I can say I want it in polar or I want it in rectangular. So I want to just say I want all these answers in polar, because that's the way that we want to get at the end. So you want to be able to get an answer, and you want to be able to get an answer in polar format. So this is our lab. This we're going to substitute for our lab today. And we're going to actually do this a little bit in class, and then 1 through 12, and then 13 through 19, I'll talk about in lecture as well. So this is phasor and vector review. You should have had this in a math class already, but you can. Got one? Everybody else did? Okay, so take your calculator, and I'm going to do this step by step with my calculator, and I'm going to give you the steps. So this is a Casio 991EX, and they've upgraded this, and this is a little bit dated, but the ones that are available basically do the same thing. That it's kind of like the Casio 991 series or whatever they call it. So it's a Casio. Mine is a FX 991EX, and they or their cohorts are about $20 in that range. So you can buy this for about $20. Anybody not be able to buy one of these or find one of these for about $20? That's the only thing you got to buy for the course. The book is free. The lab kit is free. This is it. But this is an investment of $20. That's all it is. So anyone not be able to get one, or do you have one, or do you know? Okay. So what I'm going to do is I'm going to do, you turn the button on. It says you got to go on, obviously. And then menu setup, okay? Under menu setup, you push the second one. So you have all this grid across here with, you have 4 choices, and then you have 4 more choices. You want this one right here. That is the complex. You hit enter. Okay. So you hit, basically you hit that. You hit menu setup. You get that, and you hit menu setup, and that puts you into okay, menu setup, and then that you hit equals, and then now I think you have to hit equals or something, but that puts you into that mode. Okay. Now when you type in that mode, if you see an I, you type. Excuse me. If you see a J, that you type an I. All right. So you got to do. So here I say parenthesis, and this number 1, I say parenthesis 6 plus 10I in parenthesis plus parenthesis 8 minus 2I equals. Now let's type that in and see what we get. Okay, parenthesis 6 plus 10, and then I is that in a complex mode, it is the same as what you hit in E and G, okay? The button E and G, okay? In parenthesis, plus parenthesis, 8 minus 2I in parenthesis equals. And you should get the answer 14 plus 8I. Did you get that? Yes, sir.
Does it matter if it's an I or J?
Say again?
Does it matter if it's I or
If yours says J, if that's a complex number, then that's okay. But it should be, most of them say I. Because I is the square root of -1, okay? That's the complex -1, okay? That makes it an imaginary number. That make sense? Is that okay? Do you follow me? Everybody see this? Are you having problems with it? Did you get the answer? Now, how do you get it in a polar? Yes, sir.
So you replace the J on your paper with I?
Yes. You may place it, yeah, you just say I instead of J. But when we write it in this course, we're going to write J because I means current. That's the only difference. That's why they made the change. Okay, yeah. But now let's get this into polar format. Okay, so how do you do that? Option down. So you did the option. Okay, so after this you get option, and then there's this thing in the middle that's got like this, and then like this, and then like this. Okay, you find that. Hit this button right there, the bottom button. Okay. Option, and then that down button, and then 1, and then equals. And what's your answer? 2 times the square root of 65 at 29.74 degrees, right? Now I want that not square root of something. I want to do it just as a straight number. So I hit shift equals. And then that gives me the number 16.12 at angle 29.74, blah, blah, blah. Did everybody get that? Did you get all those moves? Please copy this down or practice this, because this is exactly how I require the answer to these questions in this format, not something else. I want it like that. Okay? And it's a bunch of steps, but once you've done it about 30 or 40 times, it's imprinted in your brain, and you're pretty well. Now, I've been told that there are some slight changes to some of the calculators, that they might not do it exactly this way, but it's close. Okay? And if you can't figure it out, Chat GPT it or Gronk it, and you'll get it. Okay? So you got 12 of them. Now you do those 12, or you go up and buy this calculator and then do those 12, and then save this paper, because we're going to do the rest of these in a few days. But we'll do the rest of them. I don't want to go through the rest of them today, because I want you to get the calculator, and I want you to get this procedure down, these 12. Okay, if you can't or won't do this, this is really handicapped for this course for you. Okay, if you insist on another calculator, or a calculator that it takes you half an hour to do this, you're going to be extremely limited. I think, because I think you saw how fast I did that, right? And how quickly that answer popped. And if you can't, and if it takes you half an hour to get an answer, you're going to be asked to do a lot of these kind of questions in a test or in a quiz or whatever. So you need to be able to quickly get through this procedure. But if you do, This is an easy course. If you can do this one little thing, it makes it a so much easier course than it would be if you didn't. And I can go back to the slide rule example. The slide rule, that thing would take you a couple, 3 minutes, right? And they just get worse, right? Any questions? Good. We go to, yes, sir. No, no. I just want I just want this. You don't have it. This is all I care about. Honestly, no, nothing else. No. Any questions about this other than, just in general? Where do I buy this calculator? What do I? Now, the other thing is that I'm going to be emailing you a quiz that will be due on Tuesday. Don't panic. You're going to start getting these on a regular basis. They're pretty simple, but that's due as well as your homework. So your homework is published. There are 2, 3 problems in each chapter, and then these quizzes as well. So you're going to be getting an email, and I have not got that email ready yet, but I'll get it ready today. So you'll be getting an email later in the day, today probably, that will basically give you a problem to solve to hand in as a quiz question. Now, these are questions like what would be on a test, and I want you to be able to do one of them and like pretend it's a test, even though you're just going to be doing it at home. Okay? You need to hand it in separately, but you can work on it as a group if you want to. If you want to meet at, Joe's Bar and Grill, and I don't. It's up to you. But that is a separate thing. It's called a quiz, and I could have you do it in here in class, and I'm not really too inclined to do that. But that's how that's done. Okay. So now we're going back to chapter 10. Okay, so that's I'll give you a copy of that. And that replaces the lab today. So the lab is, we're not going to have a lab in 2380 today. This replaces it, and we'll hopefully get those kits, and then we'll have a regular lab next week. Sorry about that. I'm not pushing the button right, or else it didn't work right, or whatever. And that's why that's it. Okay, so let's go back and look at chapter 10. Any questions about chapters 8 or 9? So chapter 10 is kind of you get this in your physics class to an extent, and it's a course, talking about magnetics, and this gets into AC. So we're basically starting with AC, even though we're still in the DC book. Okay, so we're still in the DC book, but we're talking about AC, things that wiggle, things that go up and down. Okay, so this is kind of an extension on the chapter of inductors, and it introduces a concept of magnetic circuits. Okay, in this case, voltage, or the electromagnetic force, E stands for electromotive. Electromotive force, or we commonly call it V, or voltage. These are kind of synonymous, okay? So they write E is equal to d phi over dt, okay? Now, this is the standard for flux, okay? Flux is that magical stuff that goes between electrical and mechanical. If you have a DC supply, does it ever change? The answer is no, it does not change. So if in your first job, you're working in a construction area and they're all excited and everybody's working on a construction project and they send you for a DC transformer, what are you going to do? Yes, sir. Yeah, you can't find it. Why? They do not exist. There is no such thing as a DC transformer. That's like going snipe hunting. It's also like going for the wire stretchers. They send you out for the wire stretchers. What are you going to do? Same thing. Go back, come back. There is no such thing. If you stretch a wire, what did you do to it? If you stretch a wire, what happens? It gets smaller, doesn't it? Which decreases its ability to carry current. So if you have a certain gauge wire, all of a sudden you've decreased its ability to carry current. All right? So there is no such thing as a wire stretcher. There's no such thing as a DC transformer. There's no such thing as a transformer, as a wire stretcher. So these are the two. And if they send you out for them, it's kind of like going snipe hunting, that type of thing. There is no such thing. So here, the voltage is related to the change in flux. How do you get a change in something? You vary it, right? If you don't change it, it sits there and it's zero. All right? So in this case, the only way you get voltage through a transformer is if you have a changing waveform. Now, this is a changing waveform. This is also a changing waveform. This is a sine wave. Okay? And this is the typical one we use. It's a sine wave, okay? We're going to talk about sine waves in the next book, first chapter. We're going to talk about them and dissect them and all that kind of stuff. And that's why I didn't ask you to do the last part of that lab, because those questions, last part of that lab, are just that. They're dissecting a sine wave. But for this point in this course, we're just going to say the change in flux is equal to the voltage, okay? So that's how you get voltage. And that's how you get things like speakers to work, because they vibrate, because you change the current in the wire in an inductor. So these are inductor circuits, okay? These are inductor circuits and they change, okay? Electric guitar pickup is one, and a bicycle computer is one. So this is a little magnet that goes by a sensor, and every time it goes by that sensor, it gives you a blip, spike. And that's the same way as the tire, there's a thing in your tire that does the same thing, that gives you your speed. In your car, your tires in your car, they give you the speed based on a signal inside. That I don't know if it looks exactly like that, but that could be how it's done. Okay. So magnetic circuits are useful. And they're also everywhere. And I'm going to just talk about a couple and what typically happens in a circuit and how it works. And this is having to do with motors. Okay, so a motor, electric motor, an AC squirrel cage motor is nothing more than inductors. Okay, that's all it is. So when you turn it on, what happens to it? Current goes way up and then it comes down and it's stabilized. And this is called my full load amps current. What happens here? It stays constant. It doesn't rise. It just stays constant at that point in time. It stays that way forever. What happens here? Charging the the inductors, you're filling the inductors with flux. In other words, you're charging them up. You're giving them their magnetic charge. So anytime you turn on a motor, you have to accommodate for this, and then you also have to accommodate for this. So there's two tripping points in a motor circuit. One is called the circuit breaker, or motor circuit protector, MCP, or fused, but they have to be up here. They have to be higher than that rating or they will false trip. Then you have overloads that are slow trip devices that work just above that level right there. So there's two devices that work with a motor starter to actually allow it to start and then to run. So you have these guys and then you have these guys. And they both have to be there or it won't work. Okay? If you start a motor too many times in a certain period of time, what happens? You get this influx many, many, many times and the motor heats up. And if it heats up too many, if it gets too hot, it'll actually open the, it'll start to expand and it will mess it up and it'll destroy the motor. So if you have big, big, big motors, you start them too many times and per unit of time, they just give up. They don't work. So that's another thing that you have to think about. Also, this thing of there's solenoids. So you've heard of motors, now you've heard of solenoids, okay? So you say, is there anything about this chapter that is real? Yes, there is. There's some really interesting things here in this chapter. So solenoids are down, they're like this guy over here on the right, except the fact that there's a bar. So if I do this like this, there's your wrapping around and then back like this. There's a bar here and then there's a spring, okay? When you turn this on, you want this to close. That. You want it to close. You want it to attract it and to close, right? You want that to pop in, and that's what the movement of a solenoid is. It actually moves a short distance, and then when you turn the electricity off, it goes back. It goes back to its old position. So it goes back over here when the electricity is off. So, question, is it the same as a motor? And it is. It has a high current until it closes and then it comes back down like that. Same thing. So solenoids and motors are very similar. This one is exactly like what we're talking about in this course. Motors are a little different, but they do the same basic thing. They surge and then they come back. And they basically, this one comes back because this comes in. So anyway, what happens to a solenoid if for some reason or other it gets stuck? You're telling it to turn on, but it stays out in this outward position. Well, your motor, your current goes like this, and it just stays that way. And what happens? It burns up the solenoid. Because the solenoid is not built to handle this current over a long period of time. It can handle it for a short period of time, but for a long period of time, it can't. So it will burn up. There's certain types of relays that are the same way. A latching relay, which is really nothing more than a solenoid. A latching relay has two coils. Okay, there's a coil here, and there's a coil over here. And you are pulled this way, or you're pulled this way, one way or the other. It's like a switch. It's like a switch on the wall that you flip one way and it stays that way. You flip it the other way, it stays that way. Okay, so if I energize this one, it moves it over here. It'll move it over here. If I energize this one, it'll move over here. Now, what if they're both energized at the same time? It's like a sumo wrestler and an irresistible force, and what happens? The loser coil burns up. So you have to design these if you're building a latching relay circuit so that they're never both turned on at the same time. Okay? Again, real world applications of this stuff. This is not magic. This is just real stuff. Now, here we go through and we talk a little bit about the circuitry for this. And again, I don't require you, we've got a couple of problems we're going to work with this, but I do not require you to I don't think I have any I don't think I have any problems that are assigned for this, and I don't hold you responsible for this on a test. But I do want to go through it with you just a little bit so that you have it in your head. So again, let me see if chapter 10, no, in chapter 10, I just ask you to do the transformer problems. The transformer problems in chapter 10 are really, really straightforward and easy problems. 17, 18, and 19 are all I'm asking you to do. But there are some of these problems in this chapter that are interesting, and we need to spend a little bit of time on them, even though, please don't turn me off because I just said you don't have to have them on a test. But they are interesting, okay? And you do this in physics as well, and you do it again in the motors class. So I don't want to bore you, but I do want you to understand that there is a complement in the magnetic world to the electrical world. And this is this magnetoforce. Magnetic force is equal to flux times the reactance, the reluctance of the material. And then this is the force is also equal to the number of turns times the current in the coil. Okay, so these are some of the formulas that you would use in order to get this to work. And this is this thing called the H, and the magnetizing force. Now there is a relationship between force, this magnetizing force, and the flux density, and it's called this right here. B equals mu times H, where mu is the permeability, okay? And by the way, if you look at the permeability and the permittivity of a capacitor, which is what? It is, I think it's, anyway, it's, anyway, the permittivity of air and the permeability of an inductor. So this is mu and this is epsilon, okay? Epsilon and mu. There is a term epsilon naught for free air and a term mu naught for free air. For in other words, air, and you take these two terms, epsilon naught and mu naught, and take the square root of them, you get 1 over c, which is what? The speed of light. Three times 10 to the 8th meters per second. I think it's 3 times 10 to the 8th meters per second. So it's an interesting phenomenon. And how you explain that, don't worry about it. But this term permeability and permittivity and all this kind of stuff, we just kind of toss these terms around. The permittivity of capacitors, in other words, how strong are they at being a resistor to electrons going through them? So if you have something like air, they can kind of go through after a while. But if you have something like a real thick, like a rubbery substance, that type of thing, that has a real high permittivity. And here, the permeability is its ability to be magnetized. Okay? So, again, I'm not trying to impress you with a lot of knowledge. I'm just telling you that some of these things have some really interesting physical attributes. And we talk about them kind of like, well, there's another term, there's another term, there's another term. And we talk about permittivity and we talk about permeability. And yet, what do these terms really mean to you? Well, they have physical significance. Permittivity, the epsilon term, is its ability to be a good capacitor. The mu, or the permeability, is its ability to be a good inductor. Or in other words, it is magnetizable, material that is magnetizable and passes a magnetic signal through it pretty well. And what are good permeable things? What do you build motors out of? Steel. Okay? So highly permeable things are things that you can get a good high curve out of this. All right? So, what does all this tell you? There's some really interesting stuff going on out there, isn't there? We don't know about it. We don't care. In some cases, I just talked to you about the end result, but there are some really interesting things going on out there. So if you have a permeable thing, it's good at when you magnetize it, all the electrons, they stand to attention and they all go in the same direction, okay? In other words, they all stand and salute. So if you put a magnetic field in with steel, if you put a coil of wire around a piece of steel, what do the electrons all do? They all line up. They all start spinning in the same direction. Okay? They all start doing the same thing. They don't willy-nilly, or they don't do this. They all do this. So what happens after a while? Once they've all done this, once they've all lined up doing this, what happens? You saturate. Can't do it anymore. So this is why this curve up here goes like this. So for a while it says we're all lining up, and for a little bit, then we line up really, really good, and then all of a sudden they've all lined up. Can't do it anymore. End of story, done. We're all lined up. So you have this curve. So you have this kind of thing like this, and nobody really cares, but you get a magnetization to a point, and then they can't do it anymore. That's why you have bigger. If you want more, you have to make them bigger. You have to make more steel, heavier wire, bigger currents in order to get it to work. Another thing about it is what? There is a residual when you come back down this way. It's not the same as when you go up this way. This is kind of going up, coming back down. And what about this makes it interesting? Because it's residual effect. If I don't have that residual effect, I can't spin that electric motor because there's no connection between the field, physical connection. There's no wire that's going from the field to the armature. There's nothing in the armature of a squirrel cage motor to get electric current from. You have to induce it all from the field. And when you do this, and then you do this back, there's a residual. And that residual says, I can push against that residual and make it spin. And that's how a squirrel cage induction motor works. You don't have a physical connection between the armature. I mean, you have a physical connection mechanically, but not electrically, between the armature and the field. There's not there. You look at it and say, how does this thing work? It works because of this residual effect right here. you get something spinning, and then when you take that signal off, when you go the other way, there's a residual magnetization that keeps you magnetized, that keeps you going in that forward direction until you get down to here. So again, this is not something that I can't graph this. I can graph it, but I can't show you exactly. But I can tell you that we do have a coffee can, and we do this in the motors course. We put a coffee can on a spindle, on a bearing, so it can spin. You can flip it and it'll spin. It's sitting vertically. And we have coils around it, three-phase coils, and we turn them on, and what happens to the coffee can? I just gave you the clue, it spins by itself. So you're actually inducing the magnetization, you're inducing north and south coil or north and south signals onto that coffee can, and then because of this residual effect, because you're constantly changing, it's pushing. And it sits there and spins. It isn't very efficient. It spins kind of slow, not a very good motor, but the thing spins. And you look at it, how can that spin? And you say, because of this residual effect. And you get it. After a while you say, I understand how that motor works because I can see that coffee can working. I can understand why that works. Right? And it does. So again, I'm not trying to impress you. I'm just telling you that there is a reason for this residual effect. And that's why you can build an AC motor. And that's why AC motors are so efficient. Why else are they efficient? Why else do you use AC motors? Because they don't have, a DC motor has brushes. So you do, with a DC motor, have to get current onto the armature. With an AC motor, you don't. With a DC motor, because you have brushes that actually are touching, they wear out. Because they're constantly turning against that, they're pressing against that core, they wear out. So you have to replace them. You have to take them, tear it down and replace it and fix it. They can wear out. So an AC motor will not wear out nearly as quickly as a DC motor, and you don't have to do this maintenance on them all the time. Other than that, AC or DC doesn't matter that much, but that's a big difference. The AC motors, you do not have to tear down and redo every once in a while. Okay, so here are some of your steels. Different ones have different things, and then you have this equation. The magnetization force is equal to N times I over the length of the device. And then here is this, and this is now I'm going to show you an example of, here is this B. Remember I talked to you about a solenoid? Okay, there it is up close, really close. And it's just like a continuum around. You don't have to worry about, now if it's a different type of material, you have to worry about it. But it basically, this is like a complete circuit. This, on the other hand, where you have a gap, where there is a, I got a picture of it. Nope, I don't have a picture of it. But basically, if you have a gap like this, you introduce a high resistance. And that's why you have a higher current. As long as they're separate, you have a high current. When you pull them together, when they touch, in other words, they go to a low current. So a relay, solenoid do the same thing. High current, and then they go back to a low current, and they basically are the same. Relays and solenoids basically do the same thing. And you're going to work with relays toward the end of the semester. Okay, so that's kind of all that is. I'm not going to go through a lot of this, other than maybe I'll work a couple problems at the end of the chapter, but that's about it. Now, this is the part that I do want you to get. Okay. Lee, did you go through this? Did you go through the B stuff and the H stuff in 1010? Did anybody remember B and H and all that kind of stuff? Did you learn this stuff at all in 1010? No? Did you see it all in physics? Have you done it in physics? Physics, electrical physics? No? Have you taken electrical physics yet? No? You will get it in the electrical physics, and I promise you'll get it there, and I promise you'll get it in the motors class. So you get it twice. You're not being cheated by not doing those equations and having to be do it 3 times opposed to. I thought you had it in 1010. That's why I'm not doing it. But I think anyway. Now I do want you to understand about transformers. Okay. Transformers are easy, right? Write this down and put it someplace. Transformers are easy. Okay? That being said, I'm going to show you why they're easy, and then I'm going to tell you why that's all you got to remember. Very little. Okay? So I start over here with a voltage. Now, is this an AC or DC voltage? Be primary. Is it AC? Is it an AC or is it a DC? Because this little squiggle inside it's an AC. It's got to be AC. It cannot be DC. Why? The same reason at the very beginning I told you that if they send you for a DC transformer, they're sending you on a fool's errand. Why? Because you can't get voltage through, you can't get DC voltage through a transformer because it's the D of the phi, the change in the flux. And there is no change in flux for a DC value, for a DC current. There's no change. Okay? The derivative of flux with respect to T is 0 in a DC. Okay? So this teacher asked the students to say, with 4 sentences, to use the word defeat, deduct, defense, and detail. This one student raised his hand and said, I can do that all in 1 sentence. The teacher looked at him and said, how's that? Defeat or deduct went over defense before detail. So instead of defeat, it's defeat. But anyway. Did anybody get that? Did anybody? There's no grins. You're a serious class. Defeat or deduct went over defense before detail. Okay. Have you heard that before? 10 different ways? No? Okay. Sorry. Defeat, change in flux. Doesn't happen in a DC circuit, only happens in an AC circuit, okay? So that's why the squiggle. So now I've got a primary voltage, and what's the voltage over here? Because this is called V secondary, okay? It's like there's a little circuit here, but there's not. Now I put a voltage here, and I say like 10 volts, and I say, is that, and we'll explain what AC voltage and DC voltage is in a little bit. But then I do a turns ratio, like 1 to 2. So what is the voltage over here? It's going to be 20 volts. And then I've got a current, 20 volts, and a current through a resistor, R, equal, let's say 100 ohms. I can find I. I secondary is equal to 20 divided by 100, or what? 200 milliamps. All right? Now, I have a teeter-totter. 10 volts, 20 volts, 200 milliamps. Do I go up or down over here? Little, big, big, little, big, big, little. All right, so what do I do over here? Do I multiply by 2 or divide by 2? Four hundred milliamps times 10 volts is equal to 200 milliamps times 20 volts. Is that right? Does that make sense? This is why transformers are easy because you have a teeter-totter, and once you find this, you can go back and find this. That's all you got to do. You're a serious bunch. Oh, that's all it is. That's all it is. So now you know about transformers. You've got transformers in the bag. That's all you need to remember. Okay? A teeter-totter. So when I say transformer circuit, immediately you go to the teeter-totter and you say transformers are easy. I've got to have a balance on the left and a balance on the right, so that the left has to equal the right. So that this times this equals this times this. Little big, big little. You got to have a little and a big on both sides. How's that? And it's based on this ratio. So why do we have transformers? A lot of reasons. But one is because we carry voltage out in the street or out in the country at a high voltage, and we can reduce the current and still get the same power. And then we go through a transformer at your house or in the neighborhood, and we bring it down to 110, 220, or something. We bring it down to something. Maybe if you're living on a farm, we bring it down to 443 phase or 233 phase, okay? But it either single phase or three phase doesn't matter. It's the same thing. You bring it down and then you use it at a lower voltage. Could you use something at 10,000 volts? Of course. The rules are much more stringent. Why? Because electricity can jump and does jump, and it can kill you without ever touching it. All right? If you're out in a industrial park or an industrial area, and there's a fence, and it's got electric transformers and switchgear in it, how close do you walk up to that fence? Can you go up and touch the fence? You might be okay. If you touch the fence, what's the possibility of getting electrocuted? If there's a short in that circuit in that area, there's a good possibility this is electrified. How far can electricity jump? If it's a dark and stormy night and it's extremely a lot of water in the air and all that kind of stuff, it can jump about a foot per 1,000 volts. So if you've got 10,000 volts on that fence, how close do you want to get to that fence? About 10 feet. So again, it's not a big deal, but you don't walk right up to it and touch it. All right? That's why you bring it down. You bring it down to something that you can use. Now, we consider less than 50 volts safe for the most part. 110, we don't consider safe, but I've been shocked by 110 enough times that if you wear good leather shoes, rubber sole shoes, and you put one hand in your back pocket and you just touch it with one thing, it ain't going to go through you to the ground, right? It ain't going to go through you to, it ain't going to go through your heart. That's the bad thing. It's not going to do that. It can kind of maybe, ouch. And just a word to the wise, if a wire if you're working in an electrical circuit or whatever, and you pick up a wire called SP, stands for spare, what do you do to it? You don't touch it. SPs are per game, right? They can already hooked up someplace else. We just don't know what they're hooked up to. What do you do before you ever take that wire and do something with it? Touch it to a pipe. Okay, and if it arcs and sparks, that's not a spare. That's something other than a spare. All right. So at that point in time, you take it, tape it off, and say, I'm not going to touch that one. I'm going to find out what's on the other end of it. I'm going to look for another spare. Anyway, that's an aside. But why do we have transformers? So we can work with electricity. All right. Now, if you are scared of electricity, that's a good thing. That's not a bad thing. Don't be so scared that you're never going to touch an electric circuit. But on the other hand, there are changes in our outlook of electricity over the course of the last 30 years. And what used to be a hazardous profession has become a lot more less hazardous because of some of the rules that people are doing right now. And I honestly think they're good. Now, you say, why even talk about this right now? Well, because I brought the subject up about high voltage, right? And all of a sudden you're getting scared. And I'm not going to touch that. I'm going to get out of this program. I'm not getting electrocuted. Well, there's ways to never, ever have to worry about that. And some of them are pretty straightforward. If you work with 24 volts, you're never going to get electrocuted. How's that? Now, never say never, because you can get electrocuted with the 12 volts. If you're working on your car underneath and your back is against a wet ground and you touch gold ring or something like that to plus 12, it can go through your heart and kill you. It's happened. 12 volts can kill. It's extremely hard, but it can happen. 24 volts, though, is not going to kill you in any of these circuits we've got in here. It's not going to kill you. It's not going to hurt you. You'll see a little arcy, maybe a little bit, but nothing major. 110 volts, it arcs enough that it can bite. We don't let you touch 110 in any of our courses here, so we don't do that. In the real world, there are times when you do work with 110, but there are rules for working for 110 and rules for working in a panel. Most of the things that we're doing today in this outside, either 110 or 24, some of it has already been switched to 24 volts, some of it is not switched and still 110. So I don't know how to answer exactly, other than the fact that there are rules for 110, there are rules for, the rules for 24 don't really exist, but there's some rules for 110 volt that you need to abide by. But designing of panels and all that sort of thing is interesting today, because really what we've done is we say there's two sides to a panel. There's your safe side and your voltage side, what you have to have special equipment for, and that's how they deal with it. So you can deal with this. It's not that you can't deal with it, but most of the time you want to deal with it with the electricity off. But if you have to turn the electricity on, there are ways of dealing with it. It might be what they call a beekeeper's suit. Looks like a beekeeper, but it totally protects you against arc flash and all that kind of bad stuff that can happen. So again, things have changed over the last 20 years, 30 years, and what used to be a very dangerous at times profession. And I'm one that worked in this in arena when it was not safe. And I worked on a panel one night here in Toledo all night, and I was right over 230 volt transformer, and it was open, and I put a piece of cardboard over it so that I could work behind it. Do that all night. Next morning, I told the guy, I said, what you need are 4 relays, or 5 relays, whatever it was. He said, what do you need 5 relays for? I said, because that's the only way this is going to be made to work. He went out and bought them, put them in, and it worked about 2 minutes, 5 minutes, and it was in that. Anyway, I got to go home and sleep. But anyway, so transformers are dangerous. They can be dangerous, but basically they're here to transform the voltage down to something that's safe. And there's transformers for all kinds of stuff, not just for power conversion, but that's the main important thing for them, okay? So now once you've got this teeter-totter thing, this is straightforward for the most part. Now there is a center tap thing here, which basically says this splits this voltage. So if you have a voltage over here and then you've got a voltage over here, it goes across the whole thing, but then half of it goes across this and half of it goes across this. And that's typically what you have in a house. That's the household voltage, okay? Okay, so I basically told you that this part right here, and this is how this is done. You can ignore these little dots. Okay. But that's basically it. Very easy, very straightforward. Anybody scared? There's a video that I have people watch over the holidays or over the break or whatever. I've done this for years. I may in this course, I don't remember for sure, but I have it, and it's very, very interesting. A guy came here and about 10 years ago and did this 1 hour presentation. And you see people getting electrocuted, you see people getting killed by blast of copper from an arc flash. You say, who would ever want to go into that profession? And I'm reminded that, when I was working at Owens Corning, they guaranteed us that that would never happen. It's like, we're protected. And then we come back to today and they say, doesn't matter whether you say you were protected or not, you still have to wear the suit. And I think that you're much safer today than you ever were 20, 30 years ago. I would start motors. You'd always ask the question, did you measure the motor? What does measuring a motor mean? Well, it means you check phase to phase with a high voltage tester. A megger it cranks up to 500 volts and tests your insulation. So it says phase to phase, high impedance, phase to ground, high impedance. You ask the electrician, did you measure the motor? And they say yes. And I felt safe at that point in time in taking a screwdriver and taking that motor starter and turning it on with a screwdriver. And I'm exposing myself right to that motor starter. And that motor starter is what can explode if you don't have it. If you don't have the proper breaker in front of it, and if it is shorted in the back on the motor side, you get killed. I did it for years. Never thought a thing about it. And then all of a sudden they come along and say, can't do that. Why would I ever want to do that? Why would I ever want to jeopardize myself? Well, when you're doing startups, you don't always have the luxury of doing everything in an orderly fashion. So in other words, you have a control circuit, but the control circuit wasn't hooked up and working yet, but the motor was hooked up and was ready to go. And you wanted to see whether the motor was going to go forward or backward or even run at all. In other words, is this motor going to turn? So you do that, and then it's going to fall back, right? So you do that, and then when you let go, it'll fall back. So it's just like a start stop, like a real quick, just to see if it's going to. You bump the motor, and you see if it's going to turn, and then if it's backwards, what do? You flip any two wires, and then it'll go forward. You say, you did that? Yep. I would either do that or have an electrician do that. But I basically, if an electrician was not standing around, I would take the two wires and flip them around. Not hot. Turn the thing off, turn the two wires around, then bump it again. Yep, it worked. Why is that important? Because a lot of pump motors, for one thing, if you let them run for any length of time, they're on an impeller, and if they're running backwards, they'll run right off the impeller and run the motor and run the pump. So you bump and then see, did it go forward? Did it go reverse? Oh, got to flip two wires. No, I have to flip two wires. It's easy. And then you're ready for your control circuit. That's how you do it, and that's why they pay you money. You say, do you have to do that? No, and in other words, today you can't do that because you can't. Unless you have the proper suiting and all that kind of stuff. Usually let the electricians do that today. But I did all that stuff. Okay. Also climbed ladders. Scared to death of heights. You would not get me on a high, I write something at Cedar Point, my eyes closed or whatever. Hated heights. Hated them. You know what I did at Owens Corning? Motor at the top of a 165-foot batch house, way up on way up there. Have to climb up there and read the full load amps off of it, or climb up outside of a silo that would be going up, and then you have to go over whatever. But going up the side of a silo outside. Yeah, I did it. But I was scared anyway. Now this is a story. I'm going to stop the stories, but this is a story of a guy who I heard about. I never saw him, but he was going up the side of the outside of like a grain silo, but it would be a batch house for a glass furnace. One armed, with a batch with prints under his arm. So he would go up like this, he had the prints under his, like he didn't have an arm. He had lost his arm, but he would go up and he would have to let go and grab the next one and go up and grab the next one. That's that's interesting. I could never imagine that. But anyway, I'm not saying this is a dangerous profession, but I am saying that there have been dangers in the past, and I think most of them have been alleviated. I'll be blunt. I think most of them are gone. You got to be careful. You always have to think and always be aware of your surroundings. If it's uncomfortable, get out. And things can come at you from different angles. And one guy told me, he said he had lost some hearing, or he had hearing problems because of it, but he was in a room that he said he just could not hear. But he said it was just really uncomfortable because this motor was running really, but it was 10 hertz frequency. And you can't hear 10 hertz. You can hear 20, but you can't hear 10. And he said he got semi-permanent hearing damage because of that. So be careful. Always be careful. Always. And I was in a styrene plant, styrene, where they made stuff with styrene. And I said to the guys that were there, I said, "Boy, that smells bad." And the guy said, "I can't smell that." And the styrene had eaten out the nerve endings in their nose to the point where they couldn't smell it. I hate to work in this plant. So anyway, again, not to scare you, but to tell you that you've got to be careful. You just always are aware of your surroundings, wherever you're at, whatever you're doing. But in a plant, most of the time it's safe. But every once in a while you're in an area where it's just not safe, and you've got to be careful and you've got to be vigilant and just realize that. And also, if you go into a plant where they're not abiding by those rules, where you have to wear the suit and all that kind of stuff, if you walk into a plant and say, "Well, we don't do that stuff, we've been safe for so long," they're 30 or 40 years out of date, because 20, 30 years ago, these rules came into existence, and it's against the law to not go by the rules. It's against the law to not do that. So be aware of that. And if you're in a plant where that's the case, best thing for you to do is to just walk out and say, "That's not for me. I'm not going to do that." So again, I'm just telling you the reality of the world is sometimes there's people that still were 30 or 40 or 50 years ago that didn't ever switch. Called the arc flash rules. So anyway, I'm way off my subject, but I do care. So anyway, so let's go down and work a couple of these. See, I told you all that stuff so I don't have to work in these problems, because they're not hard, but they're not all that easy. Whatever. So okay. So here's how you do number one, and I'm just going to do number one. I'm not going to do a bunch of them, and I'm going to do maybe a couple of the transformer ones, but not even 17, 18, and 19. I think are the only ones we do. But I want you to be able to do the transformer problems. Anyway, so here's number one. Okay, so you have a magnetic circuit. Assume that the cross-sectional area 1 centimeter by 1 centimeter with a path length of 8 centimeters. The entire core is made of sheet steel, and there are 100 turns. Blah blah blah. Determine the current. Establish the flux. To establish a flux of 8 e to the minus 5 Webers. Okay, so in that case, B is equal to the flux divided by the area. That's one of the equations in that chapter. Okay, it's equal to 8 times 10 to the minus 5 over 0.01 times 0.01, okay? Which is equal to 0.8. Okay, so that is my B. H equals 100 for sheet steel. H times L is equal to Ni. 100 times 0.08 So I is equal to H times L over N. 100 times 0.08, which is my H. Oh, this is my length divided by 100 is equal to I, which is 0.08 amps or 80 milliamps. And that's it. Basically, that's it. Not a lot there. So again, I'm not going to try to impress you with those, but that's pretty much it. Okay. Number 15. I think this is one that I asked. The ideal transformer has a 6-to-1 voltage step-down ratio. The primary is driven by 24 volts and the load is 100. Determine the low voltage and the current and the primary side current. So this is one that I actually would hopefully that you would be able to do. So here I have 24 volts over here, 24. And then I have the transformer, and I have a resistor. The load is 100 ohms, and the step down is 6-to-1. So if I have 24 over here, what would I have over here? 4 volts, okay? So if I have 4 volts divided by 100 ohms, what do I have? 0.04 amps or 40 milliamps, right? Now you draw, if you want to, the little teeter-totter. Over here I have 4 volts and I have 40 milliamps. What do I have over here? 24 volts. A big little over here on the voltage. This has got to be the big, so I do what for the current over here? 40 divided by 6 milliamps, whatever that is. You got a big and a little, you got a big and a little. That's it. That's why transformers are easy. Now this one is a little bit more sticky in that. Okay, so now here you got 120 volt primary. You got a center tap on this side. So basically you have 120 over here, you got 36 over here, which would be what? What's the turns ratio? 120 to 36. Ten to 3, right? If I have 10 over here, I have 3 over here. So that's my turns ratio. So here I have, now each of these is attached to 50 ohm resistor. So this is attached to 50 ohm, this is attached to 50 ohm. And now I have half of 36 or 18 volts here, and I have half of 36 or 18 volts here. What is my current through each of these? It's going to be the same volt, it's going to be the same current, right? Whatever it is, it's going to be the same current. Isn't that correct? 1850. So what would be the current? What would be this I right here? What would be this I? What would be the I through that one and the I through this one? The same thing. This is the same current as this. So you use the same current here. So what would be the current in the secondary? It's 18 divided by 50 is my I of the secondary, okay? What is 18 divided by 50. 36, 360 milliamps, or 0.36 volt, but 0.36 amps. Everybody agree with that? 18 divided by 50 is 0.36, or 0.36, or 360 milliamps. So if I have 36 volts over here on my teeter-totter, I have 36 volts, and I've got 0.36 amps. Over here I've got 110 or 120. What would be my ratio over here? It is this, it's 0.36 divided by, what's the ratio of this? This is 10 to 3, so it divided by 10 over 3. That's it. Don't worry about the split one. Don't worry about it, but that's how it's done. Worry about number 15. And also number 17. Don't worry about number 16. But that's how it's done. But number 17 and 15 are the two that you need to be able to work. All right? And that's it. I rambled enough today, and I again, I apologize for not doing more with the B and the H stuff, but hopefully you got some ideas as to why we deal with this electric stuff. And hopefully it didn't scare you. And we're not gonna do a lab today, other than you're gonna work those first 12, get your calculator, and hold on to that sheet, because we're gonna work the rest of those later when we get into chapter 1 of the next book. Hold on to that, and we'll pick up on Tuesday with chapter 1 of the AC book. We're done with the DC.